All right, let's learn about reaction rate laws. Okay, what the heck is a rate law? Well, like I told you in the last video, how the reactant concentration affects the rate of reaction, we have to do that experimentally. All right, so we have to run through a whole bunch of things in a lab to figure out what happens to the rate depending on the concentration of things. So once we do that, we can write an equation. Right, so this equation is something we call a rate law. So it's this relationship between the rate of the reaction and the concentration of the reactants. Right, it's called a rate law. They usually look like rate equals something, 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 and I'm going to show you what that is later on here. But it's going to be for that specific reaction at one particular temperature. It's really, really specific. For giggles. All right, so let's say we have this equation right here, this reaction right here. Hydrogen, nitric oxide. No, that's nitrous oxide. No, it's nitric oxide. Nitric oxide. I'm going blank on what that was. NO. Let's just call it NO. So H2 and NO, they react to form nitrogen and water. All right, we're going to go to a lab and we're going to figure out what happens to the rate when we change the concentration of things. So first thing we're going to do is just run this reaction, see how fast it goes. Then we're going to do it a second time. We're going to keep the concentration of NO exactly what it was in the first reaction. So we're not going to change anything. We're not going to change the temperature, not going to change the size of the beaker. Like, it's going to be run exactly the same. The only thing we're going to change is the concentration of hydrogen. And then we'll see what that does to the rate. And then we're going to do it again. All right, we're going to keep everything the same and just change the concentration of hydrogen again. And when you do that, what we see is that when we double the concentration of hydrogen, the rate doubles. When I triple the concentration of hydrogen, the rate triples. If I quadruple this, the rate quadruples. If I cut it in half, the rate cuts in half. If I make the hydrogen 1/10 of what it originally was, the rate is 1/10 of what it originally was. Ooh. So that's telling me that the rate of this reaction is directly proportional to the concentration. Right, this is alpha. This little alpha means proportional to. All right, so the rate is directly proportional to my concentration. Whatever I do to that concentration, it does to the rate. Now I'm going to keep on experimenting. So now I'm going to hold hydrogen concentration steady. I'm not going to change it at all. I'm going to change this and see what it does to the rate. All right, I'm going to do a whole bunch of experiments. And when I do that, I find that when I double the NO concentration, the reaction rate quadruples. When I triple this, it's, whatchamacallit, 9 times faster. If I quadruple it, it's 16 times faster. If I cut it in half, it's 1/4. If I may have a third, it's 1/9. All right, it's not the same as the hydrogen, right? It's got a much stronger effect on it. In fact, it's related to the square of the concentration, right? So the rate of this reaction is proportional to the square of the concentration. So when I double it, 2 squared is 4. The rate's 4 times faster. If I triple this, 3 squared, right? It's 9 times faster. That's what that means. All right, so I know how these different reactants are affecting the rate. So doing some math here, because R is proportional to the hydrogen concentration and it's also proportional to the NO concentration squared, it will be proportional to their product. All right, so I can say the rate is proportional to the concentration of hydrogen times the NO concentration squared. All right, we're getting somewhere, but this isn't super useful to have a proportionality sign in there. We want to put in an equal sign, and whenever you take out the proportionality sign and put in an equal sign, we need to bring in a proportionality constant. Dun, dun, dun. That's K. All right, K. It's a proportionality constant. So this is going to be the rate constant for this particular reaction. Usually K goes up with temperature, right? But the other stuff typically does not change as temperature increases. So as temperature increases, rates go faster. It's not that this is changing, it's just your value of K is going up. But yeah, this is called your rate constant, and it's just for this particular reaction. So every reaction will have its very own rate constant that's good for that reaction at that temperature, right? So just kind of generically writing this out. So rate equals rate constant, then you have concentration raised up to some exponent, concentration, some other exponent. If there's a third reactant in there, you might have that raised up to some exponent. All right, so yeah, this rate law is for a specific reaction at a given set of conditions, must be determined from experimental data. The exponent here, like this N and M, we call that the order of the reactant. All right, so if this was 2, I'd say it's second order in A. If this was a 3, I'd say it's third order in B. Right, that's how we're going for there. All right, the most common orders that we're going to have in our class are going to be 0, 1, and 2. So let's kind of talk about those. So if it's a first order reaction, so an order of 1 means it's first order. That means that the reaction rate is directly proportional to the concentration of that reactant. All right, so if a reactant is first order, it has a direct effect on the rate. You double it, the rate doubles. You triple it, rate triples. Cut it in half, rate cuts in half. So whatever you do to that concentration, it directly affects the rate. An order of 2, all right, so if something is second order, if I have a second order reactant, that means the reaction rate is directly proportional to the square of the reactant concentration. So if I double the concentration, I have quadruple the rate. If I triple the concentration, the rate is 9 times faster. All right, so that's what we mean by that one. There's also 0th order. All right, if something is 0 order, that means it has 0 effect on the rate. I double the concentration, it does nothing to the rate. I triple the concentration, it does nothing to the rate. All right, as long as there's some of that reactant there, your reaction will still proceed, right? But it doesn't affect the rate. And this may seem really weird, and it should seem really weird. I'll explain it in a later talk. But yeah, 0 order reactants are actually pretty common because most reactions, when we look at them, they don't happen exactly as they're written. They go through what's called a reaction mechanism. There's multiple steps. All right, and so something that's 0th order is actually a reactant in one of the fast steps, so it doesn't affect the rate. All right, let's see what else we got going here. Yeah, ooh. All right, we'll stop on this slide. So when I add up all of the orders, right, it gives me the overall order of the reactant. Or sorry, of the reaction. All right, so let's say I have this. So NO2 plus CO goes to NO and CO2. All right, so here's my reaction rate, my experimentally determined reaction rate, the rate law. So rate equals rate constant times NO2 squared. All right, we see from this, it's second order in NO2. All right, it's 0 order in CO. How do I know that? Because it's not in the rate law. So if something's 0 order, they usually don't write it in the rate law. They're not going to put things in the rate law that don't affect the rate, because that list would be almost infinite, right? So if it doesn't affect the rate, it doesn't go in. So if something's 0th order, we leave it out. So it's 0 order in that. The overall order of this thing would be 2. All right. We'll get to this last little bullet point later, but yeah, the orders in the rate law may or may not match the coefficients in the balance equation. There's a special condition when that happens, but we'll get to that later. All right, that's that for this little segment. I will catch you in the next one.